And now our one sample test for a proportion. So our test statistic is this right here, and it's p hat minus pi naught divided by the square root of pi naught times 1 minus pi naught divided by n. So notice that this looks a lot like our other test statistics. This is our sample statistic. In the numerator, we're subtracting off our null hypothesized belief of what the true proportion is, and we're dividing by a standard error. Notice that where we had p hats in our confidence interval formula, we have pi naughts now, because remember, in a hypothesis test, we're assuming that the null hypothesis is true until we find evidence otherwise. All right, so let's go ahead and do an example. CADSoft sampled 44 customers and asked them to rate the overall quality of a software package. 35 respondents thought the software was very good or excellent. In the past, this proportion has averaged about 75%. Is there sufficient evidence to conclude that this satisfaction measure has significantly exceeded 75% using a significance level of 0.05? So let's jump over to our Excel worksheet and do this example. Okay, so here we are. We're going to fill in our null and alternative hypothesis. So what's the null hypothesis and the alternative hypothesis? Well, the alternative is the one we're looking for evidence of. So what are we looking for evidence of here? We're looking for evidence that the proportion exceeds 75%. All right, so our alternative hypothesis is that pi is bigger than 0.75. And what about our null hypothesis then? Well, the null hypothesis gets the equal sign. So we can just write pi equals 0.75 for our null. All right, so we've got that handled, and now we need to figure out our test statistic and our p-value. All right, so the number of responses with a 3 or a 4 is 35. The number of observations is 44. And that would make the proportion 35 divided by 44, which is 0.7955. And what's our null hypothesized belief of what the parameter is? 0.75. So we'll go ahead and type that in there. And our level of significance, we were told to use 5%, so 0.05. So now we can compute our test statistic. Our test statistic is p hat minus pi naught. So p hat is right here, the sample proportion, 0.7955, minus pi hat, which is 0.75, and then divided by our standard error. And our standard error is pi naught times 1 minus pi naught divided by n square rooted. So let's go ahead and put the square root in here. And we need pi naught, which is 0.75, times 1 minus pi naught, which would be 0.25, divided by n, which is 44, and square rooted, and that should do it. And we get 0.6963. Now, how do we get our p-value? Well, we simply draw a picture of our z distribution. The standard normal is unimodal and symmetric, centered at 0, and we plunk down our test statistic. Our test statistic is 0.6963. And now we need to figure out which way to shade in order to get our p-value. Well, the alternative hypothesis is greater than, so we're going to shade the area to the right. Remember, the alternative hypothesis informs us which way to shade in our distribution. And we know how to get this probability. How do we get this in the normal distribution, the standard normal? We can use our norm.dist. It's the area to the right, and norm.dist gives us the area to the left. So we'll use 1 minus norm.dist. Our number of interest is our, oops, I forgot to put the equal again. Our number of interest is our test statistic, so 0.6963. Our mean in the standard normal is a 0, and our standard deviation in the standard normal is a 1. And we need to put in our cumulative equals true, and that'll give us our p-value, 0.2431. All right, so our p-value, 0.2431, is larger than our alpha. If the p is not low, the null does not go. So we're going to fail to reject the null hypothesis. And what's our conclusion going to be then? Well, did we or did we not find significant evidence for the alternative hypothesis? If we failed to reject our null hypothesis, then we didn't find significant evidence for the alternative. So we're going to say there is not significant evidence at the 5% level to conclude our alternative, which is that the satisfaction measure has significantly exceeded 75%. And that's that. So you can see that once you get your test statistic and your p-value, the game is played the same every time you do a hypothesis test. You compare your p-value to your alpha, you see if it's low enough to conclude your alternative, and then make your conclusion. All right, so back to the slides to learn about errors in hypothesis testing. All right, so we've carried out hypothesis tests. We make our decision. Are we always right? No. Are we always right in the legal system? No. Unfortunately, we let guilty people go free and we put innocent people in prison. So we have the same types of errors that can happen in hypothesis testing. In hypothesis testing, we have the truth, which is either the null is true or the null is false. And then we have our decisions over here, where we either fail to reject the null or reject the null. If you fail to reject the null and the null is true, then you've made the right decision. Accordingly, if you reject the null and the null is false, you've made the right decision. But what happens when you fail to reject the null when the null is false? Well, that's a wrong decision. If you failed to reject the null, but the null was really false, then you've made what we call a type 2 error. If you reject the null, but the null is really true, then you've made what we call a type 1 error. All right, the probability of a type 1 error is the probability of rejecting the null given that the null is true, and this is denoted by alpha. And this is called the type 1 error rate. That's how often you can expect to make this type of error. Notice that alpha is the same symbol that we use for our significance level, and that is because in most cases it is the significance level of the test. Remember that we do a hypothesis test under the assumption that the null hypothesis is true. So the probability of rejecting the null, given that the null hypothesis is true, is alpha. This should make sense. This is the significance level. It's done under the assumption that the null hypothesis is true, and if your p is less than your alpha, you're going to reject the null hypothesis. So the probability of rejecting the null, given that the null is true, is alpha. Your type 1 error rate is your significance level. All right, and then the probability of not rejecting the null, given that the null is true, is 1 minus alpha. And this is called the confidence coefficient. So notice that corresponds, those sets of events correspond to the events that lead to fail to reject in a hypothesis test are the same ones that lead to the confidence interval. All right, the probability of a type 2 error is called beta. And this is known as the type 2 error rate. It's the chance of a type 2 error occurring. And then the probability of rejecting the null, given that the null is false, is 1 minus beta. And this is called the power of the test. So obviously, we want our type 1 error rate to be low. We want our type 2 error rate to be low, but we want power to be high. That's what we want to do in a hypothesis test, right? Reject the null when the null is false. We want to find for a true alternative hypothesis, a true research hypothesis. Now, how do we control this? Well, the value of alpha is controlled. The common values are 0.01, 0.05, or 0.1. You set that value. The value of beta cannot be specified in advance. It depends on the value of the unknown population parameter. Generally, as alpha decreases, beta increases. So if you try to drive your type 1 error rate down really low, you're probably going to inadvertently increase your type 2 error rate. In the CADSoft example, our null hypothesis was that the mean time is greater than or equal to 25, and the alternative is that it's less than 25. Suppose that the true mean is 15. If we thought it was 25, but it's really 15, then there's a chance the sample mean's most likely going to be less than 25, leading us to reject the null hypothesis. If the true mean is closer to our null hypothesized belief of what the mean is, it's going to be a little harder to detect it. The sample mean may or may not be less than 25, and we would have a higher chance of failing to reject the null hypothesis. So the further away the true mean is from the hypothesized value, the smaller the value of beta. All right, so we want the power of the test to be high, and equivalently, that means we want the probability of a type 2 error to be low to allow us to make a valid conclusion. The power of the test is extremely sensitive to the sample size. Small sample sizes generally result in a low value of power, or equivalently a high value of beta. So to increase your power, you want to get a big sample size. The power of the test can be increased by taking larger samples. And then you can detect small differences between the sample statistics and population parameters with more accuracy. But remember, generally as alpha decreases, beta increases, which means what? Alpha decreases, beta increases, power is the complement of beta, so that means that power decreases. So if you choose a small level of significance, you're going to probably inadvertently decrease your power. You want to compensate that for trying to get a large sample size. And that is our end of Chapter 7, Part 1 lecture.